Okay, so I'm not going to plug in numbers, but let's talk through what these problems are asking for and how they can be solved. This one, what we have is a couple of rods, A, B, and B, C. They're welded together. It's pushed up against a spring, and this is a little bit confusing, but what they're saying is that it's going to undergo a counterclockwise rotation. So the spring is pushing against it, and it's going to spring up all the way to 60 degrees. That's the highest rotation it gets to is up to 60 degrees, and then it's going to start falling back down again. And this is asking for the velocity, the angular velocity of the assembly after it's on its way back down and it reaches 30 degrees. So let me just put a couple more figures on this. So it's pushed up against the spring pushes the thing, it rotates up to 60 degrees, at which point the velocity stops, and then it's going to come falling back down, and the question is asking what is happening at 30 degrees. For this one, ignore the spring, ignore the starting position. We're only interested in going from this, where it's reached to 60 degrees and stopped, to 30 degrees and is moving. So let's call this position 1, this position 2, and it's going to be an energy balance problem. So I have mg8 is changing, I've got rotational angular velocities is changing, we're starting from 0, and we have work and a final energy on this thing. Okay, starting from 0, so we don't have to worry about that starting energy. For our change in height, decide how you're going to define your datum for this. So what is 0, but you're looking at the center of mass of this stuff. So come out to half the length of that rod. I think the rod had, 0.4, so go up 0.2, and you have your mgh for the top piece, your mgh for the bottom piece, where it starts and where it ends. I went ahead and measured everything from kind of the center point, which would mean that the top mgh I called positive, and this negative one is underneath that connection point. So, but you're looking at the change in height for each of them. FDS versus MD theta, just a note here that you can think of this as change in potential energy, change in mgh, or you can actually think of this as a moment through an angle. So if you're looking at the moment, so I'm going from the axis of rotation to where this force is applied, and that's going to be that cross product, perpendicular relationship. So it ends up being the cosine of that angle, but then when you integrate it, it ends up being the sine of the angle. And the sine of that angle, so the distance times the sine, that is the height. So whether you think of this thing as a moment acting around where it's hinged, or you think of it in terms of mgh, either way, it's exactly the same amount. So, but mgh is probably going to be the easiest way to think through this thing. Okay, so you have your change in mgh, that's this middle term. Now let's think about the final energy that's happening at the end of this thing. Again, there's 2 different ways to think about this ending energy. I can add together for each bar the velocity of the center of mass of each bar and the 1/2 I omega squared rotation around the center. So this is one way to do it. In this case, I would be using the inertia around the center of the bar. Another way to think of this, and they're equivalent mathematically, is to, instead of using the inertia around the center of the bar, to get the inertia around the end of the bar. If you use this around the end, you no longer have to take into account the velocity of the center. So this equation, 1/2 I omega squared, 1/2 where it's the inertia around the end, gives exactly the same number as this equation, where I'm adding together the 1/2 mv squared plus 1/2 I omega squared for center versus end. So that's another, this falls out of the parallel axis theorem of relating inertias around any point if you know the inertia around the center kind of a thing. So, and again, velocity is related to angular velocity through r omega. So rather than saying the velocity of A, I'm saying r times omega, and then we have everything in terms of angular velocity. Okay, so that is that one. Start at 0, some MGHs, and add together all of those kinetic energies at the end. The last problem with gears. Everybody loves gears after that last test. Okay, so what we have, and let's just draw where we're starting, where we're ending, what are all the energies, what are all of our work. Okay, so we've got two things that we're keeping track of here. 2 kilogram uniform slender bar, so we're going to have to figure out the bar. The bar has a weight, the bar is rotating, the bar has a velocity, and we also have a gear, 4 kilogram gear B. So this gear also is rotating and falling and having things happen to it. So 2 pieces to add everything together for. Central radius of gyration, that is going to give us the inertia of the gear around the center. So this is a case where we're going to have 1/2 I omega squared, where I is around the center, as well as the velocity of the center of the gear. So 2 pieces for that energy to keep track of. And for the bar, you can either get the inertia around the center and the velocity of the center, or you can combine this to just the inertia around the end. Either way, we'll get the same thing, but it's going to start from rest, 0 starting energy. We're going to have change in MGH, and again, you can think of this as FDS, or you can think of it as MD theta and crank through the integration. Probably easiest just to think through MGH for this thing. So the bar starts here, and you're keeping track of the center of the thing. So this changes a height of the length over 2. That's how far the center of it falls. B, the change in height is actually the length of the bar that it falls. So use those for MGH. And then crank through your kinetic energies. Okay, hopefully that'll be enough to get you through those energy balance problems.